let's see the control mass approach. This is called we are filling a tank from a supply line, okay, which is a very practical problem because this all LPG cylinder or whatever compressed gas you see that is connected to a flow line, and then then this cylinder is getting charged with that gas, and that's how this takes place. So that's why it's a very practical process. So just to show you that the black line, so see what will happen. First write down. First try to understand things here itself. Let's say there is some gas. The more general case will be, I'm writing more general case. There will be some M naught in the tank. Is what? Initial mass in tank. Okay, not of tank, in tank. Initial mass of gas in tank. Fine. MF, let's say final mass in tank. So how much gas we have filled in this tank? Yes.
MF minus
MF minus N naught. Okay. So what we have filled is MF minus M naught from supply line to tank. That's what we have passed. Okay. Now, if I take a control mass approach, so if you can see that ignore the red boundary, okay, and only consider this black boundary. Let me show it in full screen mode, then you will understand. Sorry. Oh, great. Oh, I haven't put animation, but I'll do right now. I'll remove this. Okay. So what you see here is that this also I'll remove. Just see this black boundary. So black boundary is my system boundary in the beginning. Remember, we are using control mass approach. So can anyone tell me where is M naught or where is MF minus M naught? So it's a control mass approach, okay, and I am telling you what is initial M naught and what is final M naught of the tank. We also know then how much we have passed from supply line to the tank. So can you tell me that in this, so this is system boundary before charging. This system boundary before charging. Okay. So can you tell me where is M naught and where is MF minus M naught within this system boundary? Sahil, you want to try?
Yes, sir.
Yeah. Where is? Tell me where is M naught or where is MF minus M naught?
Sir, M naught is in the L-shaped pipe, and MF is in the system boundary, the tank.
No. You are getting confused. Okay, wait.
Hello.
Acha, anyone? Sneh, anyone wants to comment? Or you are not getting the question?
Sir, M naught
Sir,
is in
M naught is
the
in the
system boundary.
Yeah, so M naught is in the tank. Let's say this one. M
And
naught
MF
is here.
minus M naught is in the pipe.
The remaining, oh yeah, exactly. Somewhere, I mean, MF minus M naught. I mean, not here, throughout this. Huh? Okay. So basically, if we can use different colors, let's say this way, we can say, let me use it. If I use, let's say, gray color, then this is M naught. Okay, this is M naught. And if I use different color for, and here we have MF minus M naught. Why we are including both MF minus M naught and M naught? Because what we are taking the control mass approach, and how much mass we are enveloping in our control mass. Anyone with this? Before charging, I have shaded these two portions, right? Both are part of control mass. two components, an M naught and MF minus M naught. M naught is inside the tank and MF minus M naught is in the pipe. So how much control mass I am enveloping? Because in control mass doesn't change, that remains same. Control volume can change, the boundary
Sir,
can change.
MF.
MF, very good. You see, MF, because that's why I'm writing that M naught is inside the tank and MF minus M naught is outside the tank in the pipeline. See, pipeline is filled with the gas. I'm only taking that part of pipe so that I can get MF minus M naught. Acha, why I'm enveloping MF? Who answered? You answered correctly. Can you give some insight that why? Why we are taking MF as control mass?
So because it's the final mass. So
Very good. It is the final mass of the tank. So it's better that what is final, you have to, since ultimately the analysis will go to MF. Ultimately you have MF mass in the tank. That is the final mass of the tank. So you have to envelop it from the beginning itself. Although it's the final mass, since you are taking control mass approach, you have to envelop this mass from the beginning itself. Means from the start of the analysis itself. That's why apart from M naught, we have to take MF minus M naught also, which will finally come into the tank and get added to M naught in the envelope. Okay, very good. So our control mass in this problem is MF. And in the beginning, that MF has two parts. M naught is situated here inside the tank and MF minus M naught outside the tank. So we are taking MF minus M naught from the supply line. So I have enveloped it. Okay. So that's how control mass will look before charging. Okay. Then we'll go to another page so that you can see every time. Then after charging, this is my control mass. Okay. So let me write it so that this is system boundary before charging, and let me put an arrow so that there will not be any confusion. Insert sets arrow. Okay, let me make this also red so that you can easily connect. Color red. Okay, and this red boundary is system boundary after charging. Okay, so Sahil, you are convinced this red boundary is our final system boundary?
Yes, sir.
Why? Because ultimately everything, this whole mass will sealed in this tank,
Go
right?
into tank.
Yeah. So ultimately,
Yes.
system boundary is this red boundary after charging. And what is your control mass after charging?
MF only.
Yes, very good. I just tried to confuse you to make sure that you got this concept. Yes. So control mass is MF only. That is the whole reason we started with. Okay. So red boundary is our final system boundary. Perfect. So basically, what is happening that our system boundary is shrinking. Our system boundary and this time our system is control mass, system boundary is shrinking. Perfect. Now see how it will happen. It's very important to imagine that how it will happen. Okay, so let's say in the beginning, maybe I can use different color. So in the beginning you have this. Okay, let's make a simplified picture just to understand this concept. Let's say this is my tank. Rather than making this pipe so complicated, I'll just say that there is some gas outside. So let's say this is my MF minus M naught. Okay, and here is my M naught. Now we are compressing it. Okay, where is compression taking place? Anyone? Bhavna, where is compression taking place? Here, right?
In the
Here.
green.
Yes, here, very good. Here, 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 here. So that's how we are compressing. Okay, it's a control mass approach. So we are not going to take anything here. No. Our system boundary doesn't cross this inlet. Okay. So as Bhavana said, at the green boundary, we are compressing the gas. With what pressure? The pressure which we are maintaining in the supply line, right? So the pressure which we are maintaining in the supply line, P supply. Okay. So what is pressure here from this side of the boundary? If you want to calculate work done, I have given you a hint. We are going to use integral, means P into change in volume. When we can do that, or for what processes we can calculate the work done? It has to be quasi-static, right?
Adiabatic.
No, adiabatic not necessarily. Adiabatic, of course, it's there. Huh? I already said, means quasi-static it has to be. If you want to calculate the work done, it has to be quasi-static, right? Work done on
Okay,
the
sir.
system or by the system, whatever. Huh? So it
Okay, sir.
means, yeah, it means that from inside also pressure is almost same, because still that gas is not filled in the tank. So you don't need to consider the tank pressure. Okay, it's a very fine point, but that we have to implement. So here also at the boundary from both side pressure is almost equal, and you slightly I mean it's a very approximated analysis that we are assuming that we are compressing the gas gradually, like so that at the boundary from both sides it's always P supply. Okay, and now one can argue a lot here, but that's how this control mass is going to work. So the work done which we are going to write down, which is on the system. Okay, so if I write down work done W by system, let's say if I write. So first of all, put a minus sign because work is being done on the system. And if you take this, what I mean, if you accept this may be a point of confusion, but that's how it works. That we have to assume that P supply outside is P P inside this boundary. Then only it will be quasi-static. If you assume that, what will be the work done? So work done by system is minus, and then you can say work done on the system. What it will be? So what is so we are compressing the gas with pressure P supply. P supply. Okay. And then how much we are compressing the gas? How much is the change in the volume? Which gas is getting, which component is getting compressed? MF minus M naught, right? Not whole MF. Only MF minus M naught is getting compressed, right? And how much is the change in volume? How much this volume will change? Anyone? So what we are doing with this MF minus M naught? It had some volume and we are making it 0, isn't it? Hello? Yeah, you have to think this way, that this MF minus M naught, it is getting compressed and we will make this green boundary volume 0 finally, if everything will go to this tank. Okay, because if this mass will get accommodated in this tank volume is not changing. See, you can write this way. If you have any confusion, write this way, that let's say, since you are confused, let me put it this way, that let's say this part. Achha, what is the volume of this part, by the way? Can anyone say what is the volume of this part, green part? Yes. In the beginning, what is the value of this green part? What data you need? Tell me, I'll give you.
Specific volume.
Yes, that's it. Good. So MF minus M naught into specific volume in supply line. V supply. Okay. So this much volume is, so if you will write, let's say if you will write that, let's say if I write V initial of control mass of my system, V initial system, then what you will write? System, you will write this MF minus M naught. I'm just trying if I can convince you. V supply plus tank volume. You agree? That is my initial volume of the control of the system, which is control mass, right? And then what is final volume? Anyone of my system? Yes.
The tank volume.
Tank volume, right? Tank volume. That's why I said you that you are making this component 0, so that tank volume equal to tank volume. I mean, ultimately, so basically, the system volume is getting compressed by how much amount? This one, because tank volume is already, it will stay in the final expression also, in the final volume also. So you are compressing the gas by only this amount, right? That's what I was saying. I said it in words, but so there is a confusion among you. So this is the volume which you are removing from the system. Means you are compressing it by this much volume, so that finally it takes the tank volume. Here also you have tank volume, here also. So extra volume is this. So you are compressing this, and you are compressing the gas with this pressure. And how much you are compressing? Mf minus m naught into V supply line. So that is the work done by the system. Okay, basically work done on the system, of course. So that one thing we know, that you have to take in this control mass approach. If you find it difficult, you can take control what is it? The control volume approach. Of course, that may be more convincing. So I thought, but at least I should show you that how control mass approach works. Okay. Okay, so we know the work done by the system. Now, if we apply the first law, so with this picture, if we apply the first law, so what is our first law? First law is nothing but change in energy. Okay, if you don't remember, this is nothing but delta E is Q minus W. If you want, do you can put. Okay, so it is nothing but EF minus E naught is equal to Q minus W by system, that you know. And Q2 system, as someone said, there is no heat transfer, so Q1. Okay, so we have simply minus W by system, which we have already identified. Okay, is EF minus E naught. So our remaining work is that what is EF and what is E naught. Okay, so let's talk about E naught. So in the beginning, we have two components of the system we have seen. One is a different condition, another is a different condition. So what are those two components? First, write down those mass components. One component is MF minus M naught outside the tank. Another component is M naught inside the tank. And you want, and what kind of energy we have here? We do have any macroscopic kinetic energy? I say ignore it. Potential energy, ignore it. So what we remain with? Which kinetic energy? Sorry, which energy? I mean, which form of energy? Yeah, Snake. Internal energy, right? So multiplied by U naught. Okay, and this is anyone? This is U what? Yes, I'm waiting. This is what?
U of supply.
U of supply. U of supply. Okay, so this much, since this much is in the supply line, MF minus M naught in use. This is specific internal energy. Okay, U is nothing but capital U by M. Okay, this is specific internal energy. Okay, and this U how we can calculate, by the way? H minus PV. So you have to go to the table. If it's steam or something. Okay, so this is our E naught. Okay, U naught M naught inside the tank, and MF minus M naught into U supply outside the tank. Very good. Then write out EF. So what was the name I called? Are those persons here? I don't remember, but I have written somewhere. Shravya, Deep Joy, are you guys there? Shravya, Deep Joy. If anyone has any messaging thing or something, some app, and whatever mode, you can inform them. I would like to interact with them. Because throughout the class, if someone is online for 2 hours and not listening anything, why? Oh, I mean, there is no point of joining the class. Okay, it's just like playing with the system, which is not which I don't accept personally. I am not strict in any other regard, but in this regard, I am. I mean, don't join the class if you don't want to listen. Okay. Fine. So E note is this, U note M note plus MF minus M note is supply. Now write down E final. Okay. Let's see who will help us. E final. Okay. So E final, anyone? What is the final mass? MF. And yes, Bhavna, what we should multiply it with? Just say it.
Final specific energy,
So UF.
internal
UF.
energy.
UF. Okay. UF.
Yes, sir.
So just to make sure that there is no confusion, I'm writing down all these things. Huh? So M naught MF we have written. We should also write U naught is the specific internal energy of gas in the tank in the beginning. Okay. And UF, same thing, but at the end. Okay, fine. So we know our E naught, we know our EF, we know the work done by the system. So let's do then. Okay. So then we just need to put these quantities properly. So open a new page. Okay. And if we go to the first law, what it says that EF minus E naught is W, minus W, 2 minus W by system. So let's place it. What was my EF, MF, UF? Okay. So MF, UF minus U naught, M naught, MF. Okay. So U naught, M naught plus MF minus M naught U supply. I'll say it S. Okay. So supply I am saying by PS, VS, US. Okay. That's all. And if you want TS, S is for supply. So this is our EF minus E naught, and that should be equal to work done by system, and that we have calculated how much. That was P with a minus sign, of course. So minus. So if you see, there is already a minus sign, I guess, and there is one more minus. So minus plus. So P supply, MF minus M naught, and V supply. Okay. So there is already a minus sign. So P supply, MF minus M naught, and this V supply. Okay. So that's all we have, and if you will solve it, then it should give you, and you can check also whether it's correct or not. So we have this, we can take, so MF if I write here, all right, let's use the proper colors so that there is no confusion. So if I take MF common, okay, then we have this UF, okay, plus we have.
So can US and U not be same?
US and U not be same? No. That generalize, you cannot take generalization. See, US is the gas which is present in the supply line. So it can have different property than whatever is in your tank in the beginning. So they need not to be sent. Okay. In general, if you think, no. This we have three quantities: US, U0, UF. These all are different. U0 cannot be equal to US in general. That can be a special case. So I think if you will arrange this, let me do one thing. What we can do here, that I'm just trying to arrange it in a proper. So MF UF is fine. And this, so MF minus MF UF. Anyway, we have solved this problem already. I'm just arranging it in a nice way. M0, M0, U0. Okay. And then what we should do, that is equal to, now this, we have a minus sign here. So if I'll take this term on right hand side, this will be plus. So MF minus M0 will be common. Okay. And we will have US, and if there is any mistake, you just let me know. PS VS, right? Fine. Now is it correct? Just check. MF UF minus M0 U0, and then this. Fine, right? No mistake. Okay.
Yes.
Okay, perfect. So we finally what we are getting, MF UF minus M0 U0 is equal to MF minus M0, and this is what? H supply. Okay. So that's what H supply. So this is our equation for charging of a gas, right? Now if we go to our problem statement. So this is our final thing. From the, and we'll see it from control volume approach also, don't worry. But just if we go to our problem statement. Oh, sorry, rather than changing this, we should remain here itself, and we should change the slide. Okay. So if we go to our problem statement.
Sir,
Yes.
sir, the H supply is the specific enthalpy supply, right?
Yes, in the supply line, true. Yeah.
Okay.
Okay. Everything is specific, no doubt. Okay, because you are multiplying with mass, so there should not be any confusion. Throughout in this thermodynamic course, we are working in terms of specific quantities, because that's the table which is available in the book, in the internet, that is in terms of with respect to per unit mass. Okay. Great.
Okay, sir.
Yeah. So if you'll see our problem statement, let me open press page. See, we have a evacuated tank. So what is our M0? Anyone?
0.
Okay. So then we see how this equation becomes simplified. If we'll see, if you take M0 0, okay, then if we take M0 equals to 0, then what we left with? MF UF is equal to MF H supply. MF get cancelled, so UF equals to H supply. Okay, so with this you can easily solve this problem. So let's do that. So for a special case when there is nothing in the tank, what we got is U final specific internal energy of the tank is equal to H supply. Okay, so let's see if we can solve it. I've already written it's an adiabatic process, so Q is 0. We are neglecting kinetic and potential energy. Okay, so determine the temperature of the steam in the tank at the end of the fill. Okay, so first of all, let's calculate the supply line thing, H supply. Okay, so what will be H supply? How we can calculate it? So we have steam at 20 bar, temperature 500. So let's go to steam table and let's see 20 bar, temperature 500, whether it's superheated or why don't anyone help me? I mean, anyone? So I'm also going, we need pressure table, steam table. Oh, so first pressure, oh, we can check directly in superheated whether we are in superheated regime or not. So the temperature 20. Yeah, can anyone tell whether it's superheated or not? I already found, just to confirm.
Yes, sir, it is superheated.
Superheated, right. So because the saturation temperature is roughly 212. So if I go to now 500, so first thing which we know is that steam in supply line, it's superheated. So in that case, at 20 bar, 500 degrees Celsius, we have enthalpy, H 20 degree enthalpy, it is 3689.2, right? If anyone is checking, 3689.2, if I'm not making any mistake. 3689. Oh, no. I have taken 600. 500. Sorry. At 500, it's 3467.2. Sorry. 3467.2. 3467.2. Okay. Kilojoule per kg. Perfect. So we know H supply. So once we know H supply, we want to guess UF. So this is 3467.2. Okay, that is equal to U final in the tank. Okay, now you know that if we take the final condition of the tank, if this is the tank, final after charging, we know the pressure of the tank is 20 bar. Okay, so we know the pressure of the tank is 20 bar, and we have to find out that what is the temperature of the steam in the tank at the end of filling. So what we should do, first of all, see, we know the UF of our thing, right? We know what is UF. Now, if we want to know the temperature, can anyone tell what can be the only way?
Sir, we will interpolate in the superheated.
So first you have to guess. Right? Right. First, interpolate means you have to, how you will interpolate? Between what? You have to find out the temperature. Yes. Anyone? Any suggestion?
So we have to see where the enthalpy is reigning.
Yeah, we have to guess the temperature. Basically, we have to go. So basically, first of all, you have this H table and V table, right? Of course, for that given pressure and saturation temperature, whatever. Then you calculate a U table, and then you see whether your UF lies, and then you have to interpolate. Of course, you have to interpolate, but first you have to find out that where this UF lies, because there is no direct table of U in. Is it? If it is there, then we can give a try. Let's see. At least in my table, it is not given. So first of all, I have to calculate this. H minus PV. UF is HF minus PFVF. That I have to do. And then wherever my U lies in that regime, we have to interpolate. So let's say if you found out after the analysis that your UF lies between, let's say, U at T1 and U at T2. So how will so that you found out from the table that value of UF lies between U of T1 and U of T2. Then how will interpolate? So you know it, right? That we will simply say that U at F will be equal to U of T2 minus U of T1, T2 minus T1. Okay, this is slope multiplied by, let's say you are interpreting from T1. So U of UF minus U of T1, and then this is plus UF. Anyway, this you can do. So the only thing I'm saying that you have to guess here. So please solve this problem. I'll give you the answer and let's see whether you can guess or not. Not difficult, but it's not a direct problem. After this, thermodynamics will not help you. Then you have to go to the steam table and then you have to guess where this U will lie. So it's better you create a table of U also, okay, from the steam table, H minus PV, and then you try it. Okay, that where you like. Okay, that is one thing. Now there is a, if you take a special case, if you take a special case with the same problem, special case in the same problem, if you take an ideal gas, okay, if you take ideal gas, then what will happen? What we said, that UF is equal to H supply. H supply. Okay. For ideal gas, what we can say, H equal to CPT. It's an ideal, right? For H supply, you can say H equal to CPT. So this CP is not going to change because it's an ideal gas. So CP doesn't change and depend on situation. We have seen it in detail in this throttling thing. Okay. And UF, what we can write? UF we can write
CVT.
Yes, CVT, T in the final tank. TF tank. Okay, and this is T supply. And we know CP by CV is gamma. So basically T final in tank is equal to that. What we call this coefficient? I forgot. Does anyone remember what this PV raised to power gamma? What we call gamma?
Poisson's ratio?
No, not Poisson's ratio. Don't get confused. In this PV raised to power gamma constant, what is gamma?
Say additivity coefficient.
Adiabatic coefficient or expansion coefficient. No, adiabatic ratio. I completely forgot what this gamma is. I know it's a ratio of specific hits, but is it there is a special name or no? Well, you guys are fresher than me, so I mean, okay. So T final tank is gamma into T supply. Doesn't matter. Gamma is nothing but CP by CV. So for ideal gas, this problem becomes quite simple. But if you don't have ideal gas, then after here you have to stop and then you have to check the table and you have to guess the temperature. Okay, now let's do the same problem with control volume approach. Okay, so we have seen this problem through control mass approach. Now from control volume approach. So let's go here. In fact, we can open a new slide and then we can try to solve it. Let's try it here. So control mass is done. We have seen it. Now we will see control volume. Same problem, charging of a cylinder. So let me first make the tank. Control volume approach. Control volume approach. So we have a tank. And this is the mount where charging is taking place. So let's make down our control volume. Of course, it is just in the vicinity of this tank wall. So this is my control volume. And it's a control volume, it's not going to change. Throughout the problem, it will remain same. So this is my CV. Okay. Right. Now, let's apply the first law. So just for the recalling things, so since there is no KE, no Q, I will not write those terms. I will only write important terms. So if you write what it will be, let me. If you remember, m dot exit HE plus V exit square by 2, that is not there, plus GJD, that is not there. So no potential energy, no kinetic energy. Okay. Minus MI dot at inlet into HI, that is equal to Q dot minus WS dot minus d by dt. Okay, or d by dt. So if you can check, that was our equation. But there is no Q dot. Okay, no heat transfer, so this term gone. No work transfer, there is no soft work, nothing. Okay, so this is also gone. We have only this much. Now let's try to apply to this control volume. Okay, so when you apply to this control volume, yes, what is our m dot exit? Anyone can tell? Ayush, what do you think? What is our m dot exit? Sneh, is there any exit in this problem?
No, sir.
No, so it's zero. Zero, simple. Why there is confusion? It's zero. Gone. Okay. So we left with only this much. Minus minus get cancelled. This minus and this minus. So we only left with m dot I HI is equal to dE by dt. That's all. From this control volume approach, we are getting this. Okay. Now, if you'll see, if this is a of course, this is the mass is also balanced. Like you are not creating any mass. So if you write down the mass balance, what we can, okay, first of all, tell me what is, okay, let me write it in a different color. What will write dm by dt? Anyone? Dm by dt in this problem? Is there any outlet? Exit? No. So what will be dm by dt? Only due to this, right? Otherwise you can write this. But do we have any exit? No. So this is not there. Okay. So we have only what? Dm by dt is this. Okay. So how rate is changing? If I'll ask you how mass is changing, at what rate mass is changing inside the tank, what will your answer? Sahil, what do you think? What will your answer?
The rate at which mass is entering the tank.
That's it, simple. That's what I've written. Very good. dm by dt is simple because there is no other, there is no exit. Only mass is entering. At what rate? Mi dot. So that will be the rate of change of mass inside the tank. So this we know from mass balance. This we know from mass balance. Okay, perfect. So that's how my mass of control volume is changing at this rate. The rate at which gas is entering inside the tank. Okay, this is the entry point. Okay, this is the entry point where gas is entering. Fine. Okay, so with this, now if I'll ask you another question, is as follows: that if I ask you that what is my so if, okay, that is one thing. Now what you do, you simply do one thing. Okay, integrate both sides in this equation. And we'll integrate it from where? From 0 to T final. Let's say T final as T simply, 0 to T. Okay. So here also a dt will come. Here also a dt will come. 0 to T. Okay. What is HI? Anyone? HI is what in this case? HI is what? This is the supply line, because this is the things for the entry. Okay, so this is supply line. Okay, this is from supply. So this is nothing but H supply. I'll write it H supply, which will be outside the integration. H supply mi dot dt is equal to this dt get cancelled. It's simply d of E 0 to E. That we'll see. What does it mean by here? There is no point of limit here because now it's simply d of e is changing. So rather than we can put it in terms of this. Anyone, what should be the what limit we should put now? Because the t gone. So E naught EF of CV. Okay, of course CV because we are working as in control volume approach. So EF of CV, E naught of CV because the time limit has gone. Okay, so HS. What is MI dot? Okay, just a minute. Okay, what is MI dot DT? This I would like to hear from you.
DMDT.
Fine. So DM, you are saying MID. That's what I'm asking. That if I ask MI dot DT, what it will be ultimately?
DM.
Oh, so then integrate it. Tell me. It's very simple. That eventually how much mass you are accumulating, like adding. That's what I'm asking.
MF minus
MF minus
M.
MF minus M naught. You put the limit. No, it's very simple. What's the big deal? Huh? Mi dot dt from 0 to t is nothing but dm in change in mass. So this is going from m naught to mf. So that is nothing but mf minus m naught. Okay. So this quantity is mf minus m naught. Okay. This quantity is mf minus m naught. Perfect. Then integral of d is what? E. Fine. dt got cancelled. Integral of d is e. So this is nothing but what? EF minus EF of CV minus E naught of CV. What is EF of CV? Anyone? Final energy of the CV? MF, UF, right? What is initial energy of the CV? M naught, U naught. Okay. So what we got eventually? We got eventually HS MF minus M naught is equal to MF UF minus M naught U naught. So now let's go back to our slides, that whether we got the same thing or not. Okay. Our final equation from control volume approach is this. Let's see whether we got the same thing there or not. You can also check. So that's what we got. See, H supply MM minus M naught is equal to MF UF minus M naught U naught. Okay, so it depends on you that which approach you find easy. Okay, whatever approach you want to take in exam or in general. So for example, see why I will prefer control volume approach, because there is a line of confusion, a very thin line of confusion, that which pressure we should take for work done while taking the control mass approach, because there is always a confusion that if the gas is entering, the outside pressure is higher than the inside pressure of the tank. So why don't we take this pressure difference? But then the moment you take the pressure difference, the finite pressure difference, you cannot apply the work done formula, because that work done is defined for quasi-static work. But then if you see in the depth, if you go into the depth, you find that the work done is happening at the boundary of the system, that control mass. So inside and outside pressure are almost equal. So you have to only take the P supply. So I have just shown you that both approach work. One can take control mass approach also, but then in that case one has to be very careful. Whereas in control volume, you don't need to take any care. You just, if you integrate it properly, it works. Okay. So I show you that from both approaches we get the same answer. Okay. Then so we have done the same problem from two approach. Now you're aware. Try to practice it. Then we go to the last problem. Just discuss and then you can leave. We will do it in the next class. Just have a look and then you can. Okay, and this you can try. In fact, I'm just explaining this problem. Try, and we'll meet tomorrow. We'll solve it, and then we'll go to second law of thermodynamics. Okay, then we'll close this topic, because we have seen problem from control mass also, control volume also. We have seen simpler problem using rate equation, like in refrigerator we have solved compressor, isenthalpic process. These are just formula fitting things. The two important problem which we have seen is that charging of tank through both approaches, control mass and control volume. What is remaining is discharging of tank. That we'll also discuss in the next class, and this problem. What this problem says? So this is simply again same problem but bit twisted. Here you have a supply line. You have steam 2 megapascal 300 degrees Celsius. Okay, and this is the tank where we have this spring kind of arrangement system. Initially there is vacuum inside it. Okay, and this is at its natural length, no extension, no compression. Then this gas enters. What will happen when this gas enters? It will push the piston, and you are assuming it is happening quasi-statically, and this pressure is getting controlled by this spring force, and eventually the tank pressure in the tank becomes 2 megapascal. Okay, so we have to you have to find out various quantities. So just go through this, try to use the same approach. It's better if you go through this control volume, but you can go through control mass also. There is no problem. Whatever you find easy, you are free. Okay, that's all, guys. Thank you. I'll upload these slides. Huh? Thanks. You can leave for another lecture. अच्छा बाकी आज एक काम है, आज मेरे एक इंजीनियर आएगा, थोड़ा इक्विपमेंट शिफ्ट करना है, सौरमंडल वाला जो लोग लैब है वहां से नीचे। जो इक्विपमेंट ज्यादा बड़ा नहीं है, लेकिन वो थोड़ा सा उसको देखे ना, मेरा रियोमीटर ज्यादा बड़ा, उसको 2-3 आदमी चाहिए, थोड़ा सावधानी से आपको बोलूंगा। अभी आ जाना चाहिए, आधा घंटा 1 घंटा, ठीक है, 12 बजे ठीक, आइए लोग। कहाँ पर करना है? सबमिट 2 बार